All right. Hello, everyone. Welcome to the 8th tutorial. In today's tutorial, we're going to finish up most of the techniques that you're going to be using for your projects and the ones that you've learned in class before we move on to big data. So last week we went over clustering. Today we're going to go back to classification, and we're going to talk about k-nearest neighbor and linear models for classification. And if we have some time, I'll go a little bit into robust regression, or we might leave that for next week. So as you learned in class, there are other methods that we can use for classification. Just to recap, since last time, we learned a little bit about decision trees and how we can use entropy-based decisions for making classification rules. We also learned about naive Bayes and how we can use the Bayes formula to do classification as well. Today we're going to go back to the k-nearest neighbor, which is actually a method which some people call lazy learning. And we call it lazy learning because all you do is you just find the data points that are close to the values that you have, or to the feature values that you have, and measure the distances from all of the points, and then you just select the result to be evenly spaced between the k closest results. And intuitively, the way that it looks like is in this example. So here we used k is equal to 2. So what happens here is it will measure the distances for each of the points, and it will try and do the classification rules based off of what's the closest. You can also change the numbers or the neighbors. So in this case, with 15, the results look like this. And let's say if we bring the number down really low to 1, you can see that there's actually quite a lot more sophistication to the algorithm, as in these data points start becoming blue compared to where generally this whole area might be green. So choosing the number k is pretty important in when you do k nearest neighbor, and there isn't one right answer. The number of neighbors you should use really depends on your data set and can be selected through the methods that we talked about before, which was using a grid search when you do your parameter tuning. So and in this example, this is a very simplified case where we only have two features. If you were to have n number of features, a great number, would be very difficult to know what's the exact amount and what your data looks like. And again, the way to help try and solve that is to make some visualizations about your data. So next, what I want to do is go back to that example where we had the same data sets with the arcs, and really look at what the results for that are, just to gain some intuition on how k-nearest neighbor would work. And here again, this is if you just look at the general colors, you can see decision trees. You can see random forest, so boosted and ensemble trees, kind of get that curve shape. And if we look at something like naive Bayes, we can see here that it also classifies pretty well for this data set, but it doesn't really get those curves. If you can look at the k-nearest neighbor, it does, and that's because it's again, lazy learning is pretty effective. But this again is just is an example. Doesn't mean that k-nearest neighbor will always be better in that case. Similarly, with the circular data, you can see here naive Bayes works really well. Decision trees also are able to make a square, and k-nearest neighbor works pretty good as well. But it doesn't really get the circular part, but it still would probably give a decent score if you compare them, right? So naive Bayes in this case has a 95 accuracy, and k-nearest neighbor here has 82, and this is again just for this data set. And again, this is with kind of the linear separable data. You can look at the results, and k-nearest neighbor is also quite up there, 93% compared to 95 for the best one for naive Bayes. So as you can see here, all of the methods are pretty effective for these three different data sets. So it really depends on the parameter tuning and the assumptions that you know about your data when you're trying to decide which classifier to use. k-nearest neighbor can also be used for outlier detection. So I know that the professor just briefly touched upon it. I'm also going to briefly touch upon and not really give an example, but I will show you an example of outlier detection as well today. Using k-nearest neighbor, what you can do is if you measure the distance to the k-nearest neighbors, outliers would have a very large distance. So just by measuring that distance and seeing how many data points are close to it, you can determine if there is an outlier or not. So now let's move on to linear models for classification. And the first thing we're going to learn is about logistic regression. So again, let's try and gain an intuition for how logistic regression works. I know Professor Golab went over it briefly, but the main idea is if you have two classes or binary data, and if this is your future variable x, where it's, let's say, goes across, and your y is what you're trying to predict, and it's a 1 or it's a 0. What happens is if you have data that are part of classes and are not continuous, so again, this is not numeric prediction like linear regression, where you're trying to predict a value, like a continuous value. In this case, you're trying to predict a class, whether it's a 1 or a 0. And logistic regression is really powerful for how simple it is. I know companies like Google and many companies that are at huge web scale use logistic regression because it's a very simple and fast way to do classification compared to building decision trees and other machine learning applications. So similar to k-nearest neighbor, in performance it runs very well. So what logistic regression does is instead of fitting a linear line like the line that I showed here, if you were to use least squares linear regression, you would get a line like this, which really won't help you predict the 1 or a 0. What it does is it uses the sigmoid function. So the sigmoid function is the cumulative distribution function. So if you take a bell curve and you try and find the area underneath that curve, or the integral at each point as you move across, you'll get a nice S shape. So at very low probabilities, it'll be almost 0, and at very high probabilities, it'll be almost 100. So basically between 0 and 1. And then there'll be a sharp point where it changes. And using this sigmoid function or logistic function, you can do classification by fitting your data points onto that function. So in this case, it almost draws a line. You can think about it right here. So if the values are before this line, it would predict it that it would be a 0. If it was past this line, it would predict it as a 1. And as you can see, using it is not too difficult at all. All you need to do is just import the linear model library from scikit-learn, and then just use logistic regression, and then you can set the parameter. So again, if you wanted to learn more, I didn't show this one for k-nearest neighbor as well. If you search k-nearest neighbor, you can actually read the scikit-learn documentation here, and it gives you some great examples of where you can use k-nearest neighbor. The other thing that you can also do for doing classification is if you go to I think if you go to the documentation, what you can read is the classification guide as well as the tutorials, and they give great examples for classification and all the methods being used. So if we go back to logistic regression, or we search linear models for classification, you can actually this is for so this is actually for regression. For classification, you can read the user guide for logistic regression, and it talks about generalized linear models. Actually, it is the same documentation. It's just at the bottom. Sorry. So if you actually go down to the bottom, it explains different methods you can use for classification as well, and how you can do regression. So if we go back to logistic, logistic regression, it explains, I guess, how the sigmoid function works, and you can read in the actual documentation for what solvers to use and what parameters to use as well. So I'd recommend just reading through the documentation a little bit if you want to get some more intuition on logistic regression. You can also, that's Wikipedia. You can also look at the parameters and what regularization to use. So by reading each of the penalties and the different parameters, you can decide what to put into your grid search when you're trying to parameter tune. So if we go back to logistic regression, this is an example where I compare k-nearest neighbor to logistic regression, and it's a little bit difficult to do every single data in this one because it's classifying digits, whether it's a 0, 1, or 2. I just wanted to show this example because I want to show how simple it is to basically use k-nearest neighbor and logistic regression. So all you need to do is just load your data set, get your x, get your y. In this case, again, just for simplicity, I do a holdout. You should use cross-validation like we learned about previously. So use k-folds in addition to using a holdout. And you can simply just use k-nearest neighbor classifier and logistic regression, and you can basically get some scores. And even here, for the digits, it gives a pretty high accuracy, both using k-nearest neighbor and for logistic regression. And it runs in a couple of seconds, which is quite great, considering that the data set here is actually image data for digits. So sometimes I like to just take a look and see how k-nearest neighbor works for your data set as well as logistic regression, just to get a baseline for what scores you could get. And k-nearest neighbor can also, by making those visualizations, can also give you an idea for what your data set looks like. The next thing that I wanted to talk about is, actually this is another example using the iris data set. So using logistic regression, again, you can do it with multiple classes. And again, you can just use logistic regression directly. And here you can see using the SEPA length and the SEPA width, you can see how we split up the data set. And it is colored, but you can kind of see the color difference here, that it generally splits it into the 3 sections. Now let's move on to talking about support vector machines. And support vector machines, a lot of people use them as well because they are quite powerful. And a lot of people call it a high margin classifier. And that's because it fits a linear model and a line between the data points that creates the largest distance or the largest margin. And I wanted to show an intuition of what that looked like. So what happens is when you try and fit a line to split a data set, you can fit a line in many different ways. You can fit a line here and it will separate it, like here. There's so many different slopes you can use. Basically an infinite number between the range of fitting a line to separate the data. What the support vector machine does using linear algebra, or actually there are different methods that it does it, but it basically finds the highest margin or the largest distance between where the separation is. So if we go back here, what it does is it finds the largest distance between the line that's separated, and it fits a line based upon that. And that's really powerful because it could separate your data the best way possible, where the best way has the largest distance or the largest margin, so you can separate it pretty well. And support vector machines also are used quite often in industry, and the documentation also gives great examples of it. If you read through the documentation for support vector machines, it's quite powerful, and they're all different methods you can use as well. And I'm going to show a couple here. So this is creating a linear model where there are uneven sets of data. So here's like the red, data set, and here's sort of the red class, and here's the blue class. And if you want to create a line, it depends the method that you want to use. You can actually use weights. So if you have uneven sets of data, you can robustly do classification by setting weights. And this is an example where you can actually use that by adding a weight. So when you see the term hyperplane, what that refers to is that line that I talked about, and it's called a plane because, again, when you're dealing with n-dimensional space compared to two-dimensional, or even in three-dimensional, a line is equivalent to a plane in 3 dimensions. So similar to using linear regression with multiple features, or multi-regression, you fit a plane. In the same way, you're linearly separating your data set, in this case, using a plane. And here's another example of it. This is using a non-linear hyperplane. So the idea here is by setting the parameter for what kernel you want to use. So in this example, it uses a special type of support vector machine, but you can also specify the kernel. And the kernel, you can think about it as just the method that it uses to draw the line. So you can use a linear kernel, and that's just like a linear SVM, but you can also use other kernels that work well with other data sets that are not linear. And again, you can read about some of the different kernels, you can use here. So if you read through here, you can read about custom kernels and other types of methods that you can use. Most people use the RBF, which is the radial basis function, and that helps with data sets that are more circular. And we'll see an example of that as well. So in this case, here is an example with a linear kernel. And here's another linear kernel. And then this is the RBF. And this is a polynomial of 3rd degree. And as you can see here, the way that classification is done is quite different for each kernel. So again, there is no set rule on which kernel is the best. It really depends on what your data is. And you can test that by using a grid search or trying different methods manually, looking at the results and visualizing the way that classification is done. So the example that I wanted to give for outlier detection, and really this isn't specific to using support vector machines, is what you can do is you can do classification, and you can classify your data set and then find where the majority of the points are in those classes. And any point that lies at a further distance away could be considered an outlier. And again, outliers are very important because they can either show you garbage or gold. Garbage as in maybe there's a measurement error, or that data set doesn't really well, or that data point doesn't well represent the data set. Or they can outline gold as in very important data points to the problem you're trying to solve. So for example, if you're trying to classify the class into 3 sections, maybe the people who are slacking are doing poorly, the people who study a lot and are keeners, there might be outliers who study very little but get very high grades. And those could be an example of where you can identify a new group of individuals, or a new group of a new class within your data set based off of outliers. So that's kind of an example with using a SVM. It's kind of a little bit complicated, but I just wanted to kind of give the intuition of how you could use classification and then determine new abnormal observations compared to the learned frontier. And really, the learned frontier is just where the general points are for where the classification rule builds it. So again, I want to go back to that example where we have those data sets. So just so you can kind of compare and take a look at all of the different methods that we have covered in class. So I'd like to bring your attention to both the linear and the RBF support vector machine. So here you can see how the linear SVM works. It really draws a line to split the data. And this is probabilistic. So again, the darker the blue, the more certain the algorithm is that the classification is here. And as you can see, the linear SVM, since it's linear, doesn't really get the those curves that we drew into the data set, or the curves that are inherent within this data set. It just splits the data set into half. Again, it splits the data set into half here with the circular. And as you can see, using a linear SVM for a data set that's circular is actually not very good. So without visualizing what your data looks like, if you just decide to use the standard support vector machine function with a linear kernel, it might not well represent your data set. But it does work pretty well with the linear separable model. As you can see, if you just look at the data set in general, you might want to split it here, and the support vector machine actually does that, and it gets a pretty high score. So the other thing that I wanted to show is using RBF, and that kind of uses radials to split it. And as you can see, it can almost perfectly get those curve shapes. Same with the circles. But on a linear separable data set, it does work pretty well. But as you can see here, if there are some points that kind of move into the blue region, it is more prone to overfitting. So similar to k-nearest neighbor and even random forest, it doesn't perfectly linearly separate the data set compared to using something like a linear SVM, or even naive Bayes in this example gives a pretty high score. So again, it really depends on various different factors for which classification algorithm you should use, and you don't just have to use one. Again, you can use pipelines, and you can try multiple algorithms and see the score for all of them. Another great tool that's the scikit-learn documentation is called choosing the right estimator, or you can also search scikit-learn cheat sheet, and it kind of gives a nice little walkthrough on the different algorithms. And I mean, this list isn't comprehensive and isn't like the rules for what you should use. It'll just give you a good starting point for where you can apply which algorithm to. So again, if we try and do classification, it recommends, if you have a smaller data set under 100,000, you can just try a linear support vector machine. If it's text data, you can use naive Bayes. Even if it's not text data, you can still use naive Bayes because it works pretty well. Otherwise, you can try k-nearest neighbor because it works pretty fast as well. Otherwise, you can try other methods. Again, you can also use random forest or logistic regression as well, which isn't here. For clustering, as we learned, we can use k-means. If you have large sets of data, you can use the mini-batch k-means. And there are other ones if you know the number of categories. And then for regression, we'll talk about that soon. So let's finish up the linear models classification, and then we can move on to regression, or we might leave that to next week because we're kind of running out of time. So the next thing that I wanted to show is talking about the pipeline again. So we learned what principal component analysis was. We didn't learn about it, but if you took linear algebra, you would kind of learn about it. And again, there is dimensionality reduction techniques again. So again, there's principal component analysis, but there are other methods you can use. And principal component analysis again is it finds the main vectors which comprise your data set and reduces your data set to those main vectors. So what it allows you to do is it allows you to reduce the number of features and only choose the important features that you want to use. And here's an example where we put a pipeline where we apply principal component analysis. So in this example, we have again the digits data set, and as I showed up here with the same digits data set, you can just use you can basically just use logistic regression directly and get a result. But maybe you want to try and improve the score that you got up here just using it directly. So what a pipeline allows you to do is it allows you to try different parameters and test them all one by one. So in this case, we're going to use principal component analysis. We're going to reduce the dimensionality of our data, and then we're going to apply logistic regression. So in this case, what we're going to do is we can choose the different parameters that we want, and then again we're going to use a grid search that's going to also use cross-validation, and it's going to use the components and the different CSs. So again, the components are the different number of vectors going to be used, and then the CSs are the parameter that is used in the logistic regression. And so here again, we define that we're going to use a pipeline, and we're going to use a grid search for both of these, and then we're going to fit, and then it's going to plot the results for each of the components and show and get the best estimator. So when you run a grid search, it will search through each of these parameters. So it will try 20. It will use 20 components, and then it will try using this parameter for logistic regression. This one, 40, this, and then 64, this. And again, you can use a randomized grid search as well. You don't need to search every single parameter. Using a random, as I showed in the previous tutorial, works pretty well. And this is just a visualization of the number of components and the ones chosen. So in this case, when we ran that cross-validation grid search, it shows that the best number of components to use for principal component analysis is about 40. So we reduce our dimensionality of our data down to 40, and it gives the highest score. So that's an example of it. But this doesn't really show grid search that well. So what I wanted to do is just show you an example of the intuition behind the way that grid search works. So again, this is a very, very long example, and it's probably not that useful for you guys to use directly, but I just want to show you the intuition of it. So in this case, basically we again use the iris data set, and we use a couple different functions. Again, we use grid search. We use stratified shuffle split. So what stratified shuffle split is, it's a very useful function when in cross-validation. So again, when you do cross-validation, it's very important that you shuffle your data before you start building classification rules. It's just better to have a randomized set of data, because as you collect data, it could have a effect on the order in which you collected it in. So by using a shuffle split, you're able to shuffle your data pretty well. And again, you can use shuffled split to do the holdout method, and then so you have a testing data set that the algorithm never sees, and then on your training set, you can again break that into k-folds and use k-fold cross-validation. But what stratified allows you to do is, if you have an uneven number of classes, when you shuffle your data, it ensures the same proportion of the classes are in the split. So when you're testing and training, the proportion of the data for each is the same, which is actually quite useful, and it generalizes your test better. So again, we split the data, and then we use again a grid search. In this example, we're using a support vector machine with various parameters for the gamma and the CD2 ranges. And I recommend you read the documentation for what the different parameters are and the ranges of values. So when you build a grid search, you can use like huge amounts of of parameters, but then your grid search will take a lot longer. So reading the documentation and understanding how Python implements each algorithm and then deciding which parameters to use are pretty important. So these are just some examples, and again, it fits a classifier for each of them within that grid search. And then, so here we can see that depending on the different parameters, it split the data differently. So in the examples that I showed you, I just used a single parameter, but as you can see, using the using a support vector machine, the kernel, by changing the parameters that the kernel uses, you can get different classification rules based off your data set. And again, it's very difficult with a large number of features to know what parameters are the best, which is why you would use a grid search. And just to give some intuition of what the results of a grid search look like, here's a great example of it. So on the bottom is one of the parameters you can use, which is the gamma, and over here again is the C value that we used. And the grid search quite literally can be represented by a grid. So it tries each and every set of parameter pairs together, and you can see here on the x-axis the accuracy that you get from low to high. So in this example, using these sets of parameters gives a very high score compared to the others, and that's like a full grid search. And again, some of you guys might take optimization, probably know about operations research. This is quite different than solving an optimization problem, and the reason for that is you're dealing with real world data, and the model that you create now has to generalize for the real world data set. So there aren't optimal parameters you can use. It's all relative to the data that you have. So again, the only way to be able to do it is to test various algorithms, various parameters, and find the best one. And you can see that even machine learning applications today are improved day to day. There are researchers working on new techniques to help with image classification using deep learning and other sorts of techniques. So really understanding the fundamentals for the different types of algorithms, and more importantly, the assumptions that the algorithms use when they do the classification is very important for when you decide what algorithm to use for your projects. And again, you can spend a significant amount of time in the grid search and the parameter tuning, but I recommend that you just try and get a high enough score for now that you can present actionable insights from, than trying to get an extremely low score. And the reason being is in the real world, what's more valuable is making use of new data compared to just using old data and building very good models. So there's a trade-off. Not only is there a bias versus variance trade-off, but there's also a trade-off in your time for where you should spend. Should you spend on making a very high scoring or very accurate algorithm, or should you focus on using a method that has a lower accuracy but is easier for you to implement? So finally, what I would like to present is robust regression. When we started learning about classification, I also said that many of the algorithms we use can actually be used for regression or numeric prediction as well. And I want to just show the intuition for where they can be used. So let's begin with k-nearest neighbor. Similarly to using k-nearest neighbor, you can measure the distances between each of the data points and use classification that way. You can also do regression. Based off your data set, you can find the nearest neighbors and set a continuous value across the features that will allow you to do numeric prediction. And those are just words. So let's look at an example of that. So this is a data set that was basically derived from a sine function. And as you can see here, by setting the weights and the nearest neighbors, it will try and find the points that are in between each of the 5 data points. So for example, if you want to predict a value that has a feature here and a feature here, what it'll do is it'll find the distance between the 5 closest points. So this point, this point, this point, this point, and this point, I guess. and this is the weighted. This is like the weighted average of where it is, and this is like a uniform weight. So you can also weight it by how far each point. So you penalize points being further away, and that's using a distance weight. Or you can just do a uniform where it literally just takes the average of the 5 values without changing the weight. And again, by using a uniform, your model is less sophisticated, but it could generalize better compared to using the distance. And again, this is with k is equal to 5. And again, we can change that. If we change it to the closest neighbor, you can see that the method could overfit, as you can see here, with kind of some outliers from the general sign trend. The noise has a huge play into it, and if you use a very high, it's going to be it sometimes will give a straight line for the uniform and might not work well as well. So choosing the number of neighbors again is also kind of an art, but can be done by using a grid search and by figuring out which gives the lowest score for this example, which helps both using grid search and cross-validation. So let's talk about using decision tree regressor. So in the same way that you can use entropy to classify data, you can use a decision tree that will actually use if-then rules. Very well, it'll use a tree, but you can think of it like if-then rules as well, because you can use a tree can be represented by if-then rules, as you learned in class. So in this example, if we use the depth of the tree to equal 5, it will say if the data is between here and here, we're going to predict that the target is 0 or 0.5, and it will build a value. It'll build rules like this. So by using a very large depth, you get sophistication in your algorithm, but you could also be overfitting. As you can see here, the outliers or the error, because I did create this sign function, plays into the regression compared to using a depth of something smaller. Decision trees regression works extremely well when paired with ensembling. Again, so using random forest, you can also do numeric prediction, and it does that again by creating smaller subsets of the data and then aggregating the results using ensembling. So boosting to use, or bootstrapping to use smaller sets of data, and then ensembling. And you can use that to do regression as well if you know that your data set isn't linear. Another method that you can use is you can actually use the support vector machine and various kernels to do regression as well. This is less commonly used. I would more recommend you use curve fitting or a polynomial regression, but there are certain use cases for using a support vector machine. I'm not really an expert with that, so there is documentation for how to do it, so I decided to present it here. But I would generally recommend you use a simpler method, such as polynomial regression. The final thing that I wanted to give was a very kind of end, formally kind of all these tutorials that you can use with a very involved example. And in this example, we're going to do numeric prediction for values of images. So let's say we have a large set of image data, and we cut the images in half, where we have the top of someone's face, and we want to predict what the bottom of their face would look like. This is a very elaborate example where you can see different regression techniques being used to predict what someone's face would look like on a data set, which is kind of cool. So again, the ones that I use here are, I use linear regression, we use k-nearest neighbor. Extra trees is again a decision tree based, and we also use ridge, which is another type of regression as well, which is in the documentation. So again, we use this face data set, and again, we use different estimators, and we present the results for each of them. So here's some results with different faces, which are kind of cool. So this is the true face, right? This is like a woman's face. You can see the top and bottom, and you can kind of see how the for each of the regression algorithms work. So with decision trees, you can see that it works actually pretty well, and it's able to get where the mouth and stuff will be. K-nearest neighbor works pretty well as well. Linear regression, not so great, mostly because, of course, the data is not linear. And ridge regression works pretty well. And it's actually pretty interesting how each of the algorithms work. But even with linear regression, it still worked pretty well to get the general shape of the face. So again, there isn't one correct answer with which algorithm to use. Using a grid search and cross-validation works pretty well. So in addition, the last thing I wanted to talk about is, in addition to just using scikit-learn, there are also sometimes customized packages you can use to be able to do certain things. And it's hard to know about all of them, but again, there's stats models, which works pretty well. There's GenSim. So stats models is general statistical functions. Whoops, that's GenSim. If you use stats models, they have another great set of algorithms that you can use for that also give you more statistical outputs for the curve fits and stuff, and they're very powerful. GenSim is pretty good if you want to do document clustering. And then again, as I presented previously, Orange has great examples of various different algorithms and implementation you can use, and you can also use the interface. So throughout all these tutorials, I tried to present all of the things that I thought were important. But again, reading the scikit-learn documentation will give you a much better understanding for all the different parameters and the other techniques that were not covered.